Hello everyone, my name is Arturo Rodriguez. Today I'll be presenting my talk for the FEDSM 2020 conference from my conference paper. The clear message that I want to give in this presentation is that we're not trying to replace direct numerical simulation or RC simulation, which are physics-based type of simulations, and we're not trying to take data-driven models in order to have the same results. So we're not. What we're trying to do is we're trying to use probability distributions from data-driven simulations to see how can we predict turbulent instances of this control volume and see how can we get with this approach. So the name of my talk is Stochastic Analysis of LES Atmospheric Turbulence Model Solutions with Generative Machine Learning Models. And my name is Arturo Rodriguez, the first author of this paper and presentation. So first I want to talk about the agenda. I want to introduce the problem. So I want to know why is it impossible to predict turbulence? What is the reason we cannot predict turbulence? And how can we use the data-driven simulation to approximate or maybe predict turbulence instances of turbulence? And I want to talk about also where does the nonlinearity comes from. So then I want to talk about the turbulence testing, which is just the things that goes with large C simulations and our results of large C simulations, and see what type of controls do we get and how can we study turbulence. Then I'm going to post-process all results gathered from large C simulations, and I'm going to use it in a recurrent neural network in order to be able to predict development of the flow. Then I go to what the neural networks, which is about introduction to learning. How can we go from recurrent neural network to a more advanced recurrent neural network, which is about the long short-term memory neural network (LSTMs). And how can we use our model in order to generate turbulent instances using probability distributions for these type of simulations. And lastly, I'm going to discuss my results, and that will be it for the presentation. Uh, Now, I want to talk about the introduction to the problem. Why is it impossible to predict turbulence? So turbulence is chaotic. By rigorously definition, it's impossible to predict turbulence because it's just too chaotic. And there's ways to predict it and try to generate solutions. One of the most expensive ones is the DNS simulation, which is direct numerical simulations, but it's really expensive to do. So we cannot resolve all the scales using lower fidelity turbulence models. Then I'm going to talk about the nonlinearity. The nonlinearity comes from the viscosity. In this case, nu, which is the kinematic viscosity. Viscosity changes with temperature, and then they also have like anisotropic turbulence, which is the convective acceleration, which is the u partial u over partial t, which is the acceleration that the simulation gets. And how can we get this energy exchange from this simulation? I mean, there's an energy exchange between all of this. It becomes temperature, it becomes velocity, it changes, so there's always an energy exchange. And you will see that when it dissipates, it heats up the surface a little bit. It depends how much high velocity does it have, how much velocity does that flow has in order to be able to generate a temperature stress on the surfaces or the boundary layer. Then I'm going to talk about my configuration, which is my turbulence model, which is large A simulation model. So here I will talk about my mesh. So I try to find my mesh near the boundary because it's more difficult to capture the scales near the boundary because they dissipate. And here's a contour of my temperature plot, on my temperature contour of my simulation. And you will see that there is some shearing between the temperatures. And that's because the chaotic behavior of turbulence is just generating those shearing stresses. And then I'm going to talk about my skewness, which is really small. If you have less skewness, that means that your mesh is more structure. And my mesh quality is really high. The aspect ratio is not above 2 or any higher number. My aspect ratio, they are more orthogonal and they have 90-degree angle between them, all of them, and they don't have one side larger than the other. And now I have almost 500,000 elements. Then I'm going to talk about my large C simulation, which is a simulation of 362 seconds. And this is my temperature control. As you can see, the flow starts fluctuating. So then you have turbulence, which is generating eddies and trying to vortices in the domain. Now I'm going to talk about my post-process. So what I did is I took screens of the simulation, going from using using the one that you see previously before, using that the XY, and this one is uh, so XY, so it will be YC. So I'm using YC in order to be able to extract screens of my simulation, and just try to be in those screens between in an alphabet of letters, and see if we train a recurrent network with letters or text based, and see how can we predict using Fisher vectors. How can we predict going from a word, I mean, from letter to a letter, and just predict a word or maybe a sentence or maybe a book. So we're trying to see how can we beat this velocity into letters and try to predict the upcoming letter in the simulation. And we use a generative machine learning model in order to predict this. So we are able to we're able to concatenate and maybe voxelize the neural network of the simulation, and then be able to create letters and bin them, and be able to use these letters in order to predict more letters in the word or maybe a sentence. So first I want to talk about neural networks. So neural network has an input layer, has hidden layers or one hidden layer depending on how much hidden layers you want to have in your neural network. We will try to optimize with the number of neurons, number of layers, and had an output. So this is the activation function, which has a weight and a bias. As you can see, this goes into transformations, and it passes from an activation function to the other. It tries to converge between, it tries to update the weights and update the values going from neuron to neuron. So can we predict this without physics, just data? That's the question we're trying to address in this talk. Is learning even feasible? Can we learn that much in order to predict this data and be able to understand how can we predict chaotic data, which is impossible to predict, as I mentioned in the beginning? So then we use probability distributions. So just imagine we have red marbles and blue marbles. What's the probability that you get a red marble against a blue marble? And a blue marble probability will be 1 minus the probability of the red marbles. How can we be certain that we can predict a red marble instead of blue marble? Or how is the probability that we can predict a certain number of outcomes depending on the number of on the number of marbles? As they go to infinity, in this case we have more data, more data, more data. As we go to infinity, how can we predict a certain kind of marble in this box? So then one thing that relates the number of marbles and the probability is the Hoffman inequality. And you can see there, Hoffman inequality. So there's two kinds of machine learning models. There's discriminated and generative. Discriminated can predict quantities at given points, for example, a linear classifier, logistic regression, neural network. And we also can use the generative models, which are recurrent networks, adversarial network, variational encoders, naive Bayes, which is the conditional probability and the probability of giving a certain outcome. For example, what is the probability of x given y, and the probability of y over the probability of x, given outputting the probability of y given x. So this is a naive Bayes approach, which is conditional probability. So I'm going to talk about long short-term memory algorithms, neural networks. Sorry. Um, so a neural network can remember, and it has a cell gate and a forget gate. So you can see that in everyday language we use everyday texting on our phones, we use recurrent networks. It means that you're giving some letters or maybe some words, and you try to predict the next one. What will the next one will be? What will be the next word regarding what you have before? It tries to use Fisher vectors in order to predict between 1 and 0s. How can we jump to the other one and predict it? So just imagine that a student is trying to cheat on a test. So then it goes from one person to the other. I understood this, I understood this. That means that it's trying to pass from information between student to student. By some of the information is lost, and then some of them is acquired. So then we can explain this by Dory. He learns it, but then it forgets, and then it tries to pass it on to another person. And how much can we get out of this? How much can we understand and be able to predict the future outcome of this text-based, or maybe just recurrent networks? We could be text or numbers or any kind of thing, but we use, in this case, we use letters. How much can I trust my model? That would be the question. So just like a book, data tells a story. That means that we try to bin all these letters that we got from the simulations, and we bin them into different sections, and we try to see if we can predict this section with another section or going from one to the other, and how does it work. So then we start with a data set. We break into subsets, and then we have an input and we have a target. So we have the input, which is 1, 8, and 6, and then we try to predict in the first data set subset, we got to predict the next one. With previous data, how can we predict the following data using a recurring network? So it shuffles and then it does the LSTM. So the LSTM is given as an input set, and then it's trying to return the corresponding target set. That means that it's trying to predict the future of this data set, depending on how many numbers it has previously done, and how can we predict the next one. So we have predicted velocities, which are the main thing about atmospheric turbulence. Velocity can relate to the velocity structure function, and we can see how much the velocity changes and how much can we predict of the velocity using different rows. So we have a screen and then we have rows along the x and y, and we're trying to predict a row, which has 1200 points. So how can we predict based on those labels or based on those binnings? How can we predict the next letter? So one of the features we're trying to do with this LSTM is that want to have more data in order to be able to see we can predict better. And we have to understand the performance, and we are going to experiment with statistical properties, the size of the subsets, and then we're going to see if we can predict also the structure function for atmospheric turbulence. So the conclusion of this is that we're not trying to really simulate turbulence again. We are using pure statistics to try to predict it. And one of the things that has misconception is that machine learning is less expensive. But the truth is that machine learning is really expensive during training. Training time is almost equals to the simulation time of computational fluid dynamics. But there are two different approaches. One is data-driven, machine learning. One is physics-based, which is computational fluid dynamics. So we are not trying to replicate physics-based simulation. We're just trying to see how well does statistical probabilities predict turbulence behaviors. So in my conclusion, I want to thank the College of Engineering of the University of Texas El Paso, the U.S. Department of Energy, and the Air Force Laboratory for contributing to our efforts into this work.